Yes.
Okay, so we are given this the undirected graph. We talk about to count the number of unreachable pairs in an undirected graph, right? So given this undirected graph, undirected means that the edges do not have these directions. And then look, there are 3 nodes in the first connected component. There are 2 nodes in the second connected component. So the number of unreachable pairs we can have is 3 times 2. There are 6 pairs. Each vertex in the same connected component forms the same number of unreachable pairs, right? For example, like 0, we can form a pair, unreachable pairs, by connecting to all the vertex other than the components the vertex in, right? So look, 0, 3, 0, 4. And this, there are 2, right? And 1, 3, 1, 4, 2. 2, 3, 2, 4, 2, okay? So we talk about the depth search. So by using the depth search, we count the number of vertex in the component. So we have depth search with these, then we count, okay, so we know there are 3 vertex. There are 5 vertex overall, right? So 3 times 5 minus 3. Right? So for each connected component, we only calculate the contributions once. First component have added this contribution 3 times 5 minus 3. 5 minus 3 is the number of nodes other than the components that the vertex is. When we calculate this, then it's 2 times 5 minus 2, right? And then we need to add it together, but we need to divide it by 2, right? Because look, when we calculate this, 3 times 5 minus 3, we have counted the pair 0, 3. And then when we come to 3, we counted the pair 3, 0. So let's consider as a same pair, so we divide it by 2, okay? We also talk about this, the number of edges equals to the sum of all the degree of the vertex, right? Divided by 2. I vertex. Look, this is the in belongs to, okay? So it means the I is in the set of vertex. So how many edges?
1, 2, 3, 4, 5.
We can sum the degree of all the vertex. The degree, the number of edges connected to the vertex. Look, these we have 1 plus these 2 plus these 1, 2, 3, 3 plus these 2 plus these 2 divided by 2. 5 edges. We need to divide it by 2. We talk about this, yeah, because look, edges has 2 endpoints. We added the contribution twice, so we have to divide it by 2. The edges, this degree has been added once here and added once here, right? So for one edges, we added the degree twice. So each edges contributes to the degree of 2. That's why we divide it by 2. This is the depth search. So with this depth search, as we talk about, we can use the multiplication to add the contribution of the unreachable pairs from the one component, right? So we multiply the number of the components by the remaining of the vertex. Alternatively, we can sum up the contribution for each vertex. For example, this one. So this one can form 3 unreachable pairs. 1, 2, 3, okay? And this one, 1, 2, 3. And this one, 1, 2, 3, okay? We go through the vertex in the connected component, right? So we need to use the depth search to count the number of vertex in the component. We can add the contribution one by one, or we can just do this multiplication. That will be quicker because we know by using the depth search, we know how many nodes in the connected component, and we can just do this the multiplication instead of adding one by one, right? And if we add the contribution one by one, and that means that for each vertex, we need to do a depth search separately. In the worst case, the time complexity will be O(n) squared or OV squared. N is the number of vertex, right? Because for each vertex, we have to do this depth search to count the number of connected vertex. And in the worst case, in a undirected graph, there's only one single component. Guess what we are going to talk about today?
Breath search.
We're done breath search, okay? So what's breath search?
Is when you breathe.
Okay, so which one?
The last one.
Wrong answer. Okay, give you one more chance.
The first one.
No. So Eric is having a breakfast. Yeah? What's this? Siri. Why this guy has no hairs? This guy has no ears. Okay. Thank you for the drawing, okay? Okay, so it's this breadth. Breadth means the horizontally, as opposed to depth search, deep. How do we usually implement a
I can
breadth
do
search?
another one if you want.
No, thank you. Well, how do we implement the breadth search?
Then Q, DQ.
Q, DQ, okay? So Q, DQ, double and DQ, two sides. So it means that we can push and pop from both sides. And then all those operations are O1 constant term. DQ. Let's take a look at these three. Right? We talk about this a lot when we solving the problems of the trees, binary trees. So what's the depth search order? If we visit the left tree first, left tree, and then visit the root, the current node, and then depth search, recursive depth search root on right. Okay, so what's the order of these? Left tree, node, right.
1, 2, 4, 5, 3, 6, 7.
Okay, and how about the depth search?
1, 2, 3, 4, 5, 6, 7. Depth search left visit current.
Depth search is 1, 2, 4, 5, 3, 6, 7. Depth search is 1, 2, 3, level by level, okay? So we use the DQ. So first of all, we push the root in it, yeah? So that's 1 in it. There are two ways of doing this depth search. One way is that every time we take everything out of the queue, we empty the queue, and then we append there, we in-queue the children of all the nodes, one by one. For example, I take 1 out. What's the kid of 1, 2, 3? I push it back to the queue. Now 2, 3 are in the same level, right? So now I take everything out of the queue. So I take everything out of the queue. What's the kid of 2? 4, 5. What's the kid of 3? 6, 7. Now look, 4, 5, 6, 7 are all in the same level, right? So then I take everything out of the queue. 4, 5, 6, 7. I push the kid like nothing. That's one way. The other way is that every time we take one node out. 1, what's the kid of it? Let's take 1 out. What's the kid of it? 2, 3. Let's take 1 out. 2. What's the kid of 2? 4, 5. The next node coming out from queue is 3. What's the kid of 3? 6, 7. Now I take the 4, it doesn't have a kid. I take the 5, it doesn't have a kid. 6, 7, etc. Okay. So when we're taking kids out of the queue, it's on the left hand side. First in, first out. Right? This is called DQ. DQ. When we push the kids back to the queue, it's called in queue. Right? In queue. Define BFS. I. This is the root. Okay. So this is the same thing. If I in sim, if we have seen this node before, we just return 0. Okay, so we don't need to add it twice, the contribution twice. Sim.add. This part is the same, yeah? Answer equals 0. Q equals DQ, right? DQ, I. So why Q, why we have elements in the queue, or why, this is the same as we checking the length of the queue, why there's the element. Current equals Q dot
Pop left.
pop left. If we don't specify left, what does it mean? What's the mean?
Pop PV right.
That's right. If we don't specify the direction, you take it from the right. Okay, so
Why is it right?
the default is on the right. It's like a stack.
Because right is right.
Excellent. Right is right. Yeah. Okay. So by default, the queue, look, by default is taking from the right. It's like a stack. If we don't specify the left, it's actually a stack. Q dot pop. Pop is taking out from the right. Q dot append is pushing to the right. Pop left, append left. The advantage of using EQ over the simple list is that when we talk about the operation on the left hand side, DQ is faster. If we perform the operation on the left side on a list, on this list here, then you'll be ON linear time. We take it out from a queue, and then we need to answer plus equals 1, right? And then we need to push its kid for x.
Yes.
For x in Gi, we are iterating the vertex that connects to I, right? And then Q dot append x. Right? So we're just appending the kids of the vertex that connects to I, and then return answer. This is the basically we're just implementing this bit depth search using the depth search. Gi means that the vertex that connects to I. So G is a dictionary, right? Look, 1, 2, 3, 4. Okay. And then we have these 5 here. If we want to store this undirected graph in the dictionary, so we use the G. This is the default dictionary. So G, what does G have? G, the keys will be the vertex 1 connect the edges, has edges to 2, 3, 4, right? So 2, 3, 4. 2 have the edges to 1 and 5, right? 3 have the edges to 1. 4 have the edges to 1, okay? So look, the keys are the vertex. The values are the list of vertex that has edges to connect it to. So GI means that we're going to the vertex, right? The vertex actually has connections to. And then we append the vertex back to the queue. Right? That's breadth search, level by level. Right? In a binary tree or a tree, it's very easy to see it's a level by level thing, right? Yeah, because the tree upside down, yeah, level by level. What's level by level in an undirected graph? 1, 2, 3, 4, 5, 6. Okay, so what's the breadth search order? 0, 2, 0, 1, 2, 4, 5, 6, 3. Okay, look, because the distance, the 1 and 2 are closer. 0, 1, 2, and then these 2 nodes, level 1. Okay, and all other nodes, level 2. Okay, so it's 0, 1, 2, 3, 4, 5, 6. Okay? There might be a problem here. Because we have to check if the vertex has been visited. So we have to check here. If x not in scene, right? And then we do this q dot append and then scene dot add x. Right? So because in binary tree, we don't usually check if the vertex has been visited. We don't go back. So there's no chance to visit the same vertex twice. But in a graph, since the edges are undirected, so the vertex can be visited more than once. So we have to mark it as visited so it doesn't go back. Make sense? What's the problem and what have you learned today?
There's a graph.
There's a graph, yes?
Using breadth search.
We were given a graph, undirected graph, and what do we want to do with it?
We want to count the
Let's see.
unreachable pairs or nodes in it.
Why do we use the breadth search? What's the breadth search going to do? 0, 1, 2, 3, 4. Okay, so how many unreachable pairs? 0 here. So the breadth search and depth search, you count the vertex in this component. There are 2, right? So how many nodes altogether? There are 5. So the contribution of this component is 2 times 5 minus 2. Here, the contribution of this is what? The same. 2 times 5 minus 2. The contribution of this one is 1 times 5 minus 1. Right? We added these together. We added all these, we have to divide it by 2, remember? That's it for today. Bye-bye. We are given an undirected graph. We want to count how many unreachable pairs from each other, right? So look, the node, yeah? 0, 1, 2, 3, 4. This is the undirected graph. What's the difference between undirected graph and directed graph?
Undirected graph has no direction.
That's right, no direction. So it means that both way, the edges coming and go for the both way, right? The directed graph, right? 0.
Arrows.
Yeah. So it means that 0 can go to 1, but not 1 go to 0, okay? And we also talk about the formula. The number of edges equals the sum of the degree for all the vertex. I belongs to all the vertex, okay? So this is the formula. B is the sum of the degree. For the directed graph, the degree consists of 2 parts. The incoming and outgoing, right? Incoming is the edges, number of edges going into a vertex. The outgoing degree is the number of edges going out. For example, this one. This is the directed graph, yeah? The in degree for the vertex 1 is how many edges going into 1?
1,
1. How many edges coming out from 1?
2.
2, yeah. Okay, so the in degree will be 1. Out degree will be 2. And the degree for 1 is 3, 1 plus 2. Okay, for the directed graph. For the undirected, it doesn't have direction, so the degree for any vertex is just the number of the edges. So for the degree for the vertex 0 is 3, there are 3 edges. So the sum of all the degree for the vertex equals the number of edges. Let's take this example. Yeah, 0, 1, 2, 3, right? 0, 1, 2. Right? There are 3 edges. The sum of all the degrees. 2 plus 2 plus 2. Yeah, that's 6 divided by 2 is 3 edges. Why we need to divide it by 2? We talked about that, right? Because for one edge there are 2 endpoints. And 2 endpoints means that the degree has been added twice. Right? So look these edges. We added 1 degree for this vertex 0. We added another degree for the vertex 1. Okay, so we divided by 2. This part is adjacent list. We usually use the adjacent list to represent the graph data structure. The G, default dictionary. The keys are the vertex. The values are the list of the vertex that it has edges to, right? Okay, so let's adjacent list. Look, 0, 1, 2, 3. Look, 0, the vertex 0 connects to 1, 2, 3. There's another concept called weighted or unweighted graph. What's weighted? Weighted means that you have this label cost for the edges. So we can label the edges or the cost. For example, like 1, 2, 3. Means that from 0, it costs 1 to go to 1. From 0, it costs 2 to go to 2. From 0, it costs 3 to go to 3. That's weighted, yeah, weighted. If we don't have this weight over the edges, then that's unweighted, and we can think of it as uniform. That's each weight, the cost of between the edges are uniform is 1. We can use the adjacent list to store the weights as well. Instead of simple list of vertex, we can use the tuple. Yeah? So for example, 0 to 1 is 1 and 1, 1. Okay, 0 to 2 is 2 is 2, 2. Okay, 0 to 3 is 3, 3. Okay, we're using the recursion to implement the depth search. For each component, we only calculate it once. Right? That's why we have this if seen. We check if it has been visited. So if we are looking at this, right, we count there are 3, and then we mark the vertex in the same component visited. So the next time we don't add it again, right? We can add the contribution for each vertex separately. They will be taking a little bit slower, right? So look, 0, how many pairs? 2. So it means that 2 plus 2 plus 2, right? So for each vertex, if we do the depth search, it probably needs to take another n times if there are n number of vertex. So the time complexity, if we count it, if we added the contribution for each vertex in the same component separated, that's going to take on squared, right? OV squared. Okay, V is the number of vertex, right? But instead, for each component, we just do it overall once. So there are 3. So we use 3 times 2. So any question about this part? That's good. Okay, so this bit, this is the adjacent list. Yeah, we're converting the edges to adjacent list. Okay, so now today we're going to talk about the breadth search. What's breadth search? Do you still remember what's breadth search?
It's when you eat.
No, not the breadth first. Breadth first. What's breadth first?
It's when you use key.
Yeah. So it's level by level. Okay, so we talk about breadth search, BFS, a lot when we are solving the problems of the trees. The trees are a graph, right? Tree is a graph. What's the breadth search order?
0, 1, 2, 3, 4, 5, 6.
Yeah, level by level. We use a queue, okay? And if we use the depth search, visiting the left tree first, yeah, depth search left, and then visiting the root,
1, 4, 5.
and then depth search right, okay?
1, 4, 5, 0.
0, 1, 4.
0, 1, 4, 5, 2, 6, 3.
We are done. Okay. And then we usually use the recursion to implement the depth search, but we also talk about using the stack, right? Using the stack. We use the queue, double-ended queue in Python to implement the breadth search. So how would you do it? First of all, we put the 0, the root in that, right? There are 2 ways of implementing a breadth search. One way is look 0. I take everything out from the queue, DQ, yeah, and I push it to kit. Is 1, 2, 3, 1, 2, 3, and then I take everything out and push the kits one by one. I take it out, and then the kit for the 1 is 4, 5, the kit for the 2 is 6, the kit for 3 is nothing. So 4, 5, 6. Okay, that's one way. Another way is we take one node at a time. So 0, we take it out, we push its kit is 1, 2, 3. Then the next node to take out is 1, right? Take a 1 out, its kit is 4, 5. Push it back to the queue. 2, we take it out, push its kit, 6. Right? 3, we take it out, it doesn't have any kit. 4, we take it out, doesn't have any kit. 5 and 6, etc. We just need to convert these to breadth search. the rest will be the same. Define breadth search the I. First of all, the same, yeah? If I in scene, then we just don't calculate it again, return 0. So if I in scene, return 0. It means that, look, for all the vertex in the same component, we only calculate it once. Because look, we have added 3. 3 times 2. When we were doing this depth search on this vertex 0, we added the contribution of the number of pairs unreachable is 3 times 2. And then when we go to this vertex again, do we need to add the contribution of 3 times 2? No, because we have been adding it. So we will skip the nodes, skip the vertex in the same component. Okay, so that's the same thing here. So scene, this is the same. Scene.add I. Okay, and then Q. How do we use the Q in Python?
DQ.
DQ. What's DE mean?
Double-ended.
Double-ended Q. Okay, therefore we declare a double-ended Q and we push the first node, which is I. Right, that's the root node. Answer equals 0. So actually answer equals 1, right? Because if we reach at this point, we at least have one vertex in the component. Okay, so answer equals 1. Why Q? Why we still have the vertex? Why Q means that why we have elements in the Q. So why there is at least one vertex in the Q. This is the same thing as y length Q bigger than 0, right? Or y length Q, okay? Current equals Q dot top left. Yeah, you mentioned about this. That means that, look at the Q, top left, we're taking the element from the left hand side. Okay? If we don't specify left, Q dot top, what does it do?
Right side.
The right side. Append from the right hand side. Append left from the left hand side. So basically, if we specify the left, it's from the left. If we don't specify, it's on the right. Okay? Two sides, yeah? Double-ended means that, look, the Q is two sides. It's like a pipe. Okay? You can take from the left, append from the left, take from the right, append from the right. Okay? So both sides. So the 4 operations, O1 constant term. Current Q dot top left. Actually, let's make this 0 and answer increment here. Answer equal plus equal 1 for x in G, the graph, yeah? G current. So that means that we want to iterate over the vertex connects to the current, right? And then we just do this. If x not in scene. If we haven't seen this vertex before, then we push it back to the Q. Q dot append x, and then we mark it as scene. So scene dot add x, and at the end we return answer. So the rest will be the same. C will be the number of vertex in the component, and then we do this C times n times C. We sum C n minus C. Sum C minus C. So C is the number of vertex in the component. N minus C is the number of vertex not in the current connected component. Then that's the total number of pairs, unreachable pairs, right? Because all the vertex in the current component can be connected. So look, this is all the nodes here, right? All the nodes. There are 3 nodes here. Look, there are 2 components. Maybe I add another more here, 2. So I'm visiting the nodes in this component here, right? So look, all these vertex, there are 3. I can connect any node here in these components to all other nodes, right? So I can make a connection, right? So each node will be able to contribute to these number of edges, unreachable edges. So we just need to multiply that. C is the 3. And minus C is all other nodes, right? What have you learned today? Come on.
About counting the unreachable.
What's the problem and what's the thing we learned today?
Graph.
That's a graph, undirected graph, yes?
And you want to count the unreachable pairs.
Of vertex. We want to count the number of unreachable pairs.
Using breadth search.
Yeah, we're using breadth search. What was the algorithm we used last time? Depth search. It's quite similar, yeah? Quite similar. Just different ways of traversing the graph. Traverse the nodes in the graph, okay?